Time is a concept we think about daily, yet its intricacies remain largely mysterious. Why does time only move forward? This question delves into profound theories and philosophical ponderings. Scientists and philosophers alike have long grappled with the notion of time's unidirectional flow, often dubbed the arrow of time. At its essence, this concept explores the fundamental nature of time itself, a dimension pivotal to our comprehension of the cosmos. Time isn't merely the ticking of a clock or the passing of seasons, it's woven into the very essence of the universe. Together with space, it forms the foundation of our reality. Einstein's theory of relativity revolutionized our understanding of time. It revealed that time isn't a uniform force affecting everyone equally, rather it's relative, bending under the influence of gravity and high speeds. This revelation means time behaves differently for an astronaut in space compared to someone on Earth. This isn't just theoretical. It's been proven through precise experiments, such as those involving atomic clocks on fast-moving aircraft. Physicists view time as intertwined with the fabric of the universe, a notion both familiar and deeply intricate. On a basic level, time measures events from past to future. However, this definition only scratches the surface, especially in the realm of physics. Classical mechanics, which deals with larger objects at slower speeds, portrays time as a constant progression, unaffected by the universe's state. Einstein's theory of relativity transformed our understanding of time dramatically. Instead of being a standalone concept, time became part of a larger structure called spacetime, a four-dimensional framework. According to Einstein, time can stretch or dilate under the influence of gravity or high speeds. This phenomenon has practical implications, as seen in the faster ticking of clocks on satellites compared to those on Earth due to weaker gravity in orbit, a crucial consideration for systems like GPS. In the realm of quantum mechanics, where particles' behavior at the smallest scale is studied, time assumes a different role. Unlike in relativity, where time can bend, in quantum mechanics, it serves as a backdrop for particle interactions. Combining these two successful theories, quantum mechanics and general relativity, into a unified framework remains a significant challenge in physics. Physicists also explore the idea of time having a quantum nature, leading to intriguing theories like loop quantum gravity. This theory suggests that time, like space, is composed of tiny, indivisible units, challenging the continuous flow of time we experience daily. Time is fundamental to our universe, intricately intertwined with its essence. In physics, our universe is described using four dimensions: three of space, length, width, and height, and one of time. This fourth dimension allows us to perceive the progression of events, from the smallest particle interactions to the grandest cosmic phenomena. Time's fundamental nature is closely tied to its relationship with space, forming the concept of space-time central to Einstein's theory of relativity. In this framework, time is inseparable from the three spatial dimensions. They are interconnected and influence each other. This relationship is particularly evident in phenomena like gravity. According to general relativity, massive objects warp the space-time around them, creating what we perceive as gravity. This warping affects not just the motion of objects through space, but also the passage of time. Near massive objects where space-time is highly curved, time moves slower compared to regions where space-time is less curved. While this effect may seem small in our daily lives, it has been precisely measured using instruments like atomic clocks. Additionally, time serves as a crucial dimension for the laws of physics. It provides the framework for understanding the sequence of events and the causality governing physical processes. Without time, concepts like motion, velocity, and energy would lose their significance, as they rely on the change and progression that time facilitates. In cosmology, time acts as a timeline for the universe, from its inception in the Big Bang to the present and beyond. The universe's age, estimated at around 13.8 billion years, serves as a measure of time that aids in comprehending the various stages of cosmic evolution, from the formation of the first atoms to the emergence of stars and galaxies. The nature of time delves into profound philosophical inquiries. For centuries, thinkers have debated whether time is an inherent dimension of the universe or a construct of human perception. This discussion transcends physics. touching upon the essence of reality and our perception of it. The notion of the arrow of time is a captivating aspect of our cosmic comprehension. It signifies time's unidirectional flow, progressing from what we perceive as the past through the present and into the future. Beyond philosophical contemplation, this concept is deeply ingrained in the physical laws governing our universe. Central to the arrow of time is the second law of thermodynamics, which asserts that in a closed system, overall entropy, or disorder, tends to increase over time. This principle provides a tangible explanation for time's direction, elucidating why natural processes generally transition from order to disorder. Consider a cup of hot coffee in a cooler room. As time passes, the coffee's heat disperses into the surrounding air, causing it to cool down. This process is irreversible. The coffee won't spontaneously heat up again under normal circumstances. This one-way progression from order to disorder, from hot to cold, vividly illustrates the arrow of time. In cosmology, the arrow of time carries intriguing implications. The universe originated with extremely low entropy during the Big Bang and has since progressed toward higher entropy. This escalating entropy defines time's direction on a cosmic scale, distinguishing the ordered past of the early universe from the increasingly disordered future. From a quantum mechanics perspective, time's flow lacks an inherent direction. The basic laws governing particle interactions are mostly time-symmetric, meaning they remain unchanged if time is reversed. This symmetry raises questions about why the macroscopic world, governed by these laws, displays a clear arrow of time. Resolving this gap between the microscopic and macroscopic realms is an active area of research and debate in physics. Is time's forward progression a universal principle? While our everyday experiences align with time's relentless march from past to future, the fundamental laws of physics, especially at the quantum level, don't necessarily support this unidirectional flow. In classical physics, time is viewed as a steady stream moving uniformly, unaffected by the observer's motion or position in the universe. Despite the apparent consistency in our observations, the true nature of time's progression remains a topic of significant investigation and contemplation in both physics and philosophy. This perspective aligns with our intuitive grasp of time. However, Einstein's theory of relativity introduced a nuanced view, revealing that time can stretch or slow down in the presence of strong gravitational fields or high velocities. Despite these intriguing properties, relativity doesn't negate time's one-way progression. It simply alters how we perceive and measure its passage. The real challenge to the notion of time's unidirectional flow arises from the realm of quantum mechanics. Here, at the atomic and subatomic scale, the fundamental laws governing particle interactions exhibit time symmetry. This means that the equations describing these interactions remain valid regardless of whether time runs forward or backward. In this microscopic domain, time lacks a preferred direction. This symmetry starkly contrasts with the macroscopic world, where the second law of thermodynamics dictates an increase in entropy over time, reinforcing the one-way arrow of time. So, is time's forward motion a universal law? The answer isn't straightforward. In the observable world we inhabit, time indeed appears to progress in a single direction. This is evident in the increasing disorder and aging of objects and living beings, aligning with the laws of thermodynamics and shaping our understanding of the universe and our role within it. Yet, at the quantum level, where the universe's basic elements operate, time's directionality isn't straightforward. The time symmetry in quantum mechanics implies that, in principle, time could flow in either direction. Bridging this gap between macroscopic and microscopic understandings of time stands as one of modern physics' significant challenges. The notion that time always progresses uniformly is deeply ingrained in our daily lives. However, in the realm of physics, time's passage isn't fixed but rather variable, subject to change under specific circumstances. This idea, though initially perplexing, lies at the core of Einstein's theory of relativity. Einstein's theory, a revolutionary force in our comprehension of time, suggests that time's flow is influenced by gravity and velocity. A notable illustration of this is gravitational time dilation. In regions with a powerful gravitational pull, like those near massive celestial bodies such as planets or stars, time actually passes more slowly compared to areas with weaker gravity. While this effect may seem negligible in our everyday experiences, it becomes significant in extreme environments like those near black holes, where gravity is immensely strong. The stronger the gravitational force, the slower time progresses. Additionally, velocity also affects one's experience of time according to Einstein's special theory of relativity. As an object accelerates, time for that object slows down relative to an observer at rest. This phenomenon, termed time dilation due to velocity, becomes noticeable only at speeds nearing that of light. Consider astronauts aboard a spacecraft traveling at exceptionally high speeds. They would age slightly slower than people on Earth. This isn't merely a theoretical concept, it's been verified through experiments such as observing the decay rates of fast-moving particles and comparing clocks on speedy aircraft with those on the ground. These occurrences highlight that time doesn't progress uniformly throughout the universe, rather, its flow is flexible, influenced by factors like gravity and velocity. This realization holds profound implications for our understanding of the cosmos. It challenges the idea of absolute time, a universal clock ticking at the same rate for all, and presents a more dynamic perspective, where time intertwines with the essence of space itself. The query of whether time could ever reverse its course captivates both scientists and philosophers. In our daily lives, time appears to move in only one direction, forward. This unidirectional flow is so ingrained in our perception of reality that the notion of time moving backward seems akin to science fiction. However, as we explore the realms of physics and cosmology, the answer becomes less definitive and more captivating. From a classical physics standpoint, the concept of time reversing lacks support. The laws of classical mechanics governing everyday objects exhibit time as symmetry, functioning in only one direction. This asymmetry aligns with our observation of the arrow of time, where events progress from past to future in a sequence, and phenomena such as aging or the cooling of a hot object seem irreversible. In the realm of quantum mechanics, the rules are far from straightforward. Many fundamental equations in quantum mechanics exhibit time symmetry. They work the same whether time moves forward or backward. This symmetry suggests that, at a microscopic level, the possibility of time reversal cannot be entirely dismissed. However, this doesn't imply that we should anticipate witnessing time-reversed events in our everyday lives. The macroscopic world, guided by the second law of thermodynamics, ensures that processes like breaking a glass or spilling coffee don't spontaneously revert. The concept of time reversal also emerges in certain advanced physical theories and hypothetical scenarios. For instance, in the concept of a closed, time-like curve as predicted by general relativity, specific conditions theoretically permit an object to revisit its own past. However, such scenarios often entail extreme and speculative conditions, like the existence of wormholes or cosmic strings, remaining firmly within the realm of theoretical physics. Furthermore, the notion of time moving backward raises profound questions regarding causality, the relationship between cause and effect. If time could reverse, the fundamental causal structure of our universe, where causes precede effects, would be compromised. This not only challenges our understanding of physics, but also fundamentally questions our perception of reality. Theories explaining why time moves forward stem from both physics and cosmology, providing diverse perspectives on this fundamental aspect of our universe. One central theory revolves around the second law of thermodynamics, which asserts that in an isolated system, entropy, an indicator of disorder or randomness, tends to increase over time. This rise in entropy lends direction to time, shaping what we perceive as the arrow of time, pointing from the past to the future. As per this law, natural processes generally transition from ordered states to disordered ones. For example, when a building deteriorates over time or a hot cup of coffee cools down, these processes signify a move towards increased entropy. Such increases are statistically more probable than decreases in entropy, like the spontaneous reconstruction of a collapsed building or a cold cup of coffee reheating on its own. It's this statistical likelihood that imparts a forward direction to time, rendering it highly improbable, though theoretically not impossible, for time to reverse. Another theory tackling the forward flow of time relates to the conditions at the universe's inception. According to the Big Bang theory, the universe originated in a state of exceptionally low entropy. Since then, the universe's entropy has steadily increased, delineating the direction of time. The initial low entropy state of the universe remains somewhat enigmatic, sparking ongoing research and debate. Why the universe commenced with such low entropy and why it follows a trajectory of increasing disorder are questions that persistently captivate scientists. In the realm of quantum mechanics, the explanation for time's forward motion becomes more intricate. Quantum mechanics, in several interpretations, permits time symmetry. However, in the macroscopic world, we observe a distinct arrow of time. Some physicists suggest that the act of measurement in quantum mechanics, where a quantum system is observed and defined, may influence the creation of the arrow of time. When a quantum system is measured, it selects a state from multiple possibilities, a process that could contribute to the unidirectional flow of time experienced in our daily lives. Another theory, cosmological time, ties the direction of time to the universe's expansion. As the universe expands, it evolves, transitioning from a highly ordered initial state to a more disordered one. This expansion correlates with the flow of time, proposing that if the universe were to begin contracting, the arrow of time might reverse, a scenario more theoretical than practical in current cosmological understanding. The relationship between entropy and time's direction stands as a crucial concept in comprehending why we perceive time to progress forward. Entropy, usually described as a measure of disorder or randomness within a system, lies at the heart of the second law of thermodynamics. This law posits that in an isolated system, entropy tends to increase over time. This upward trend in entropy is what gives rise to the arrow of time, the perception that time progresses from the past to the future. To grasp how entropy ties into the direction of time, consider a straightforward illustration: a box holding a mixture of gases. Initially, if the gases are segregated, with one type on each side, the system exhibits low entropy. It's highly ordered. As time elapses, these gases naturally intermingle, leading to a state of higher entropy or increased disorder. Once mixed, it's highly improbable for the gases to spontaneously revert to their original segregated state. This unidirectional shift from low entropy to high entropy mirrors our experience of time moving from the past to the future. Moreover, the correlation between entropy and time's direction plays a pivotal role in understanding the universe's history. According to the Big Bang theory, the universe originated in a state of exceedingly low entropy. Since then, the universe's entropy has been on the rise, delineating a temporal trajectory from the highly ordered early universe to the more disordered current state. The cosmic rise in entropy offers insight into why we retain memories of the past but not the future, and why cause and effect appear to unfold in a singular direction. In our daily experiences, the principle of increasing entropy manifests in various phenomena, such as the cooling of a cup of coffee or the rusting of iron. These processes all trend towards higher entropy and typically irreversibly progress under normal circumstances. This irreversibility serves as a macroscopic representation of time's arrow. However, it's essential to recognize that the relationship between entropy and time is nuanced across different contexts. In the microscopic domain of quantum mechanics, the fundamental laws mostly exhibit time symmetry, meaning they don't inherently favor a specific time direction. This prompts intriguing inquiries into why the macroscopic world, grounded in these microscopic laws, displays a distinct time direction. Einstein's theory of relativity introduces the captivating concept of time dilation, which elucidates that time isn't a fixed experience but can vary based on speed and gravity. This theory revolutionizes our comprehension of temporal dynamics, departing from the idea of a uniform universal clock ticking for all. Simply put, time dilation implies that time can elapse at varying rates in different circumstances. Two pivotal scenarios where time dilation becomes significant include proximity to massive objects with strong gravitational fields, gravitational time dilation, and travel at extremely high speeds, relativistic time dilation. Let's delve into gravitational time dilation first. As per Einstein's general theory of relativity, time progresses more slowly in regions with stronger gravitational fields. This phenomenon occurs because gravity can warp space-time, and the closer an object is to a massive body like a planet or star, the greater the curvature of space-time. For instance, a clock situated on Earth's surface where gravity is stronger will tick at a slower rate compared to a clock aboard a high-flying airplane. Although this effect is minute in everyday life, it's measurable and holds practical significance, such as in the functioning of the GPS system, where satellite clocks adjust for these disparities to offer precise positioning. The second type, relativistic time dilation, arises at high velocities, as elucidated in Einstein's special theory of relativity. When an object moves at velocities approaching the speed of light, time elapses more slowly for it relative to an observer at rest. For instance, if one were to travel aboard a spacecraft nearing light speed and then return to Earth, they would discover that less time has passed for them compared to those who remained on Earth. This scenario, often depicted in science fiction as the twin paradox, has been experimentally confirmed using precise atomic clocks aboard fast-moving aircraft and in particle accelerators. The ramifications of time dilation are profound. It underscores that time is a malleable concept influenced by factors such as velocity and gravity. This flexibility challenges our conventional perception of time as a constant and uniform progression, unveiling a universe far more intriguing and dynamic. Understanding the role of time in the Big Bang theory is pivotal for comprehending the universe's evolution. This leading explanation for the universe's origins suggests that approximately 13.8 billion years ago, the universe emerged from an exceedingly hot and dense state and has since been expanding continuously. In this context, time emerges as a pivotal dimension that traces the narrative and evolution of the universe. At the genesis, during the initial moments following the Big Bang, time played a decisive role in sculpting the cosmos. According to the theory, as time unfolded from that inception, the universe underwent a process of cooling and expansion, culminating in the genesis of fundamental particles and eventually atoms. This gradual cooling and expansion facilitated the emergence of celestial bodies like stars, galaxies, and other cosmic formations. A prominent aspect of time in the Big Bang theory lies in its correlation with the cosmic timeline, a chronicle detailing significant events in the universe's history. For instance, approximately 380,000 years post-Big Bang, the universe had cooled sufficiently for electrons and protons to merge, forming neutral hydrogen atoms, a pivotal phase termed recombination. This milestone allowed photons or light particles to traverse space freely, resulting in the cosmic microwave background radiation observable to this day. Another vital function of time within this framework is in comprehending the universe's expansion rate. By gauging the velocities at which galaxies drift apart, astronomers can extrapolate backward to estimate the universe's commencement, yielding the current estimate of 13.8 billion years. This expansion, however, isn't static, but fluctuates over time, influenced by phenomena such as dark energy, a mysterious force propelling the universe's expansion to accelerate. Time also holds significance in contemplating the universe's future within the Big Bang theory. According to prevailing understanding, the universe might perpetually expand, potentially leading to the prospect of the universe's heat death. In this scenario, the universe expands to such an extent that it cools drastically, nearing absolute zero temperature, with all dynamical processes grinding to a halt. So how do black holes reshape our grasp of time? These cosmic marvels, born from the remnants of colossal stars, wield such immense gravitational force that they twist space-time, altering the passage of time nearby. This phenomenon offers a distinct lens through which to explore how gravity influences the temporal fabric. At the perimeter of a black hole lies the event horizon, a boundary beyond which nothing, not even light, can evade capture. The gravitational tug in proximity to a black hole is so potent that it markedly decelerates time relative to an observer situated far from the black hole. This phenomenon, termed gravitational time dilation, stems directly from Einstein's theory of general relativity, which posits that massive entities like black holes can distort the very essence of spacetime. Consequently, time near a black hole elapses much more sluggishly than in its distant environs. For instance, were a clock to approach the event horizon of a black hole, an observer situated afar would witness the clock ticking progressively slower until it seems to halt upon reaching the horizon. This phenomenon bears captivating implications. For instance, if an astronaut were to orbit in close proximity to a black hole before returning to Earth, they would perceive that less time has elapsed for them relative to those who remained on Earth. This isn't merely a hypothetical scenario, it's a tangible demonstration of how gravity can perturb the temporal flow, albeit on a scale far more extreme than our daily encounters. Moreover, black holes provoke a speculative reconsideration of time. Certain theories suggest that the gravitational might of a black hole could contort space-time to such an extent as to fabricate conduits, referred to as wormholes, to alternate points in both space and time. While wormholes presently dwell in the realm of theory and spark considerable debate, they unfurl intriguing conjectures concerning the essence of time and space. Furthermore, the exploration of black holes has sparked inquiries into the ultimate destiny of information and matter engulfed by them. This inquiry bears ramifications for our comprehension of time and the bedrock principles of physics, notably the tenet of information conservation. The conundrum regarding whether information engulfed by a black hole is irrevocably lost, dubbed the information paradox, holds profound implications for the essence of time, causality, and the fundamental mechanics of the cosmos. In the quest to scrutinize the directionality of time, numerous experiments and observations in physics have proven pivotal. These endeavors delve deep into the core attributes of time and its progression, particularly concerning entropy and the precepts of thermodynamics. Among the most noteworthy experiments are those that scrutinize the behavior of particles at the quantum scale. In these investigations, physicists scrutinize how subatomic entities such as electrons and photons interact across both forward and reverse temporal scenarios. The principles of quantum mechanics governing these particles predominantly exhibit time symmetry, implying that they should behave analogously irrespective of whether time progresses forward or backward. Experiments conducted with particle accelerators, for instance, have affirmed the constancy of the fundamental interactions of these particles under this symmetry. These findings hold pivotal significance in elucidating time's directional flow, intimating that at the most fundamental stratum, the laws of physics may not exhibit a predisposition toward a singular temporal direction. In another area of study, researchers focus on understanding the entropy of closed systems. These systems, which are isolated from their surroundings, are essential for investigating the second law of thermodynamics. This law asserts that entropy, a measure of disorder, tends to increase over time within such systems. This increase in entropy is significant because it underpins the concept of the arrow of time, indicating the directionality from past to future. For example, experiments observing the movement of particles in a fluid or the cooling of a heated object consistently demonstrate this rise in entropy. These experiments reinforce our understanding of the arrow of time. Moreover, cosmological observations contribute to testing this directionality. Astronomers and physicists analyze phenomena such as the universe's expansion, cosmic microwave background radiation, and the distribution of galaxies to track the universe's evolution over time. These observations align with the Big Bang theory, which suggests that the universe originated from a highly ordered state and has since transitioned towards greater disorder. Furthermore, there are theoretical proposals for more direct tests of time's directionality. Some physicists have proposed experiments to explore the concept of closed time-like curves derived from general relativity, where time loops back on itself. However, these ideas remain primarily theoretical and have yet to be realized through practical experiments. Quantum mechanics presents a fascinating challenge to our understanding of time, departing from the linear progression we're accustomed to in classical physics. In classical physics, time flows steadily from past to future. But in the quantum realm, things get a bit more complicated. One way quantum mechanics shakes up our notion of time is through its core principles and equations, which are largely symmetric with respect to time. This means that whether time moves forward or backward, the rules governing quantum particles remain the same. Unlike our everyday experience, where events follow a clear cause and effect sequence, quantum mechanics doesn't pick a preferred direction for time. Moreover, quantum mechanics introduces the concept of superposition, where particles can exist in multiple states simultaneously until observed. This blurs the straightforward timeline we're used to, as it suggests that until we measure them, particles haven't definitively evolved into a particular state. Consider Schrödinger's cat. Until we peek inside the box, the cat is both alive and dead, challenging our conventional understanding of time's progression. Quantum entanglement adds another layer of complexity. When particles are entangled, the state of one directly influences the state of another, regardless of distance. Changes in one particle happen instantaneously in the other, hinting at a connection that seems to transcend the constraints of time and space. This instantaneous entanglement challenges our linear view of cause and effect, raising questions about the very nature of time itself. Some interpretations of quantum mechanics, like the Wheeler-DeWitt equation in quantum cosmology, propose a universe where time isn't a separate dimension at all. According to these models, time only emerges under specific conditions, challenging the idea of time as an essential backdrop to all physical processes. Now, let's delve into wormholes. These are a theoretical concept in physics that blend space-time and gravity in a captivating way. Often likened to shortcuts or tunnels through the fabric of space-time, wormholes spark curiosity among scientists and science fiction enthusiasts alike. In physics, a wormhole is a hypothetical connection between two distinct points in space-time, potentially enabling faster travel between them compared to conventional space travel. The concept of wormholes stems from Einstein's theory of general relativity, which explains gravity as the result of space-time curvature caused by mass and energy. While wormholes are solutions to the equations of general relativity, it's crucial to note that they remain theoretical and haven't been observed in reality. Regarding their connection to time, wormholes open up intriguing possibilities. If they were to exist, they could theoretically facilitate time travel. This possibility arises from the theory of relativity, which suggests that space-time could be curved in a manner that not only links different locations in space, but also different points in time. Consequently, traversing a wormhole might not only transport you to a different place in the universe, but also to a different moment in time. However, the notion of time travel through wormholes presents numerous scientific and philosophical hurdles. A significant challenge is the necessity of exotic matter to maintain the stability of a wormhole. Exotic matter, a hypothetical form of matter with negative energy density and negative pressure, is not currently known to exist in the required form. Without this exotic matter, a wormhole would collapse so rapidly that it would be impractical for travel. Furthermore, the concept of time travel through wormholes introduces paradoxes, notably the grandfather paradox. In this scenario, a time traveler could potentially alter past events in a way that prevents their own existence. These paradoxes pose substantial challenges to our understanding of causality and the fundamental nature of time. So, can we truly travel through time? The idea of time travel has long captivated both scientists and the public, often appearing in science fiction. However, certain aspects of modern physics suggest that time travel could theoretically be possible, albeit with significant limitations and obstacles. The foundation for contemplating time travel lies primarily in Einstein's theory of relativity. According to general relativity, the intense gravitational field of a massive object can distort space-time around it. This distortion affects the passage of time, a phenomenon known as gravitational time dilation. In theory, if one were to orbit near a massive object like a black hole without succumbing to its gravitational pull, time would pass at a slower rate for them compared to someone farther away from the gravitational field. While this isn't time travel in the sense depicted in science fiction, it does imply that time can elapse at different rates in different regions of the universe. Another theoretical avenue for time travel arises from the idea of wormholes, which are solutions predicted by the equations of general relativity. A wormhole theoretically connects distant points in spacetime, and if manipulated correctly, could potentially enable travel backward in time. However, the practical challenges of this are immense. Creating and sustaining a wormhole would necessitate exotic matter with negative energy, a substance not yet observed in the required form. Furthermore, even if such a wormhole could be engineered, concerns persist about its stability and safety for traversal. On the other hand, traveling to the future is theoretically more plausible than journeying to the past. Special relativity posits that as one approaches speeds close to the speed of light, time dilates, effectively allowing for a leap into the future. However, the technological barriers to achieving such velocities currently exceed our capabilities. Traveling backward in time presents additional hurdles, not just in terms of technology, but also concerning physics and causality. The prospect of retrograde time travel introduces paradoxes, like the well-known grandfather paradox, which challenge our understanding of cause and effect. Additionally, most physicists contend that the laws of physics likely prevent backward time travel to circumvent these paradoxes. Now, considering the concept of the end of time through a cosmological lens, we venture into a domain where science grapples with the profound mysteries of the universe. One captivating theory in this realm is the notion of the Big Freeze. This theory, grounded in the fundamentals of thermodynamics and the ever-expanding universe, suggests that as the universe continues to stretch, it will gradually lose heat. The pace of expansion driven by enigmatic dark energy, which accelerates this growth, holds a crucial role in this scenario. The Big Freeze envisions a future where stars deplete their nuclear fuel, resulting in a cosmos devoid of their light and warmth. As galaxies drift apart and stars fade away, the universe will edge closer to absolute zero, a theoretical temperature where all motion halts. This gradual cooling process, unfolding over trillions of years, signifies not just the fading of stars, but the cessation of all known physical processes that sustain life and structure in the cosmos. Alongside the Big Freeze looms the notion of heat death, where entropy, the measure of disorder in a system, peaks. In this state, no energy remains available for work, and the universe reaches thermodynamic equilibrium. Everything becomes uniform, devoid of temperature variations or energy gradients necessary for change or the existence of life as we recognize it. Another intriguing scenario is the Big Rip, which foresees a more dramatic conclusion. The Big Rip theory pivots on the behavior of dark energy. If dark energy intensifies with time, it could tear apart everything from galaxies to atoms. In this vision, space-time itself would undergo relentless stretching until its ultimate demise, resulting in a universe where distances between all points become infinitely vast. On a philosophical level, these theories prompt us to contemplate the essence of time and existence. They serve as a reminder that the universe operates on scales and principles far beyond our everyday experiences. Whether through a gradual descent into cold oblivion or a cataclysmic unraveling, the envisioned end of time by cosmology paints a portrait of a universe vastly different from the dynamic cosmos we presently inhabit. Exploring the boundaries of our current comprehension of time, particularly within the realms of cosmology and scientific inquiry, leads us through a labyrinth of intricacies and puzzles. Time, an indispensable element of our daily existence, assumes an increasingly mysterious demeanor when scrutinized through the lens of advanced physics. A primary hurdle in grasping time lies in its fusion with space. Within the framework of spacetime, a cornerstone of Einstein's general theory of relativity, we encounter a revolutionary insight into gravity. This theory elucidates that massive objects warp the fabric of spacetime, generating what we perceive as gravity. However, this amalgamation of space and time begets profound inquiries, particularly regarding time's intrinsic essence. In the domain of quantum mechanics, time's treatment diverges sharply from its portrayal in relativity. Quantum theory, governing the behaviors of particles at minute scales, regards time as an immutable backdrop, in contrast to the dynamic fluidity depicted in relativity. This discrepancy presents a formidable conceptual obstacle in physics, commonly termed the problem of time. It stands as one of the foremost challenges in formulating a theory of quantum gravity, a framework aimed at synthesizing the principles of quantum mechanics and general relativity. Further complicating matters is our subjective perception of time. Human consciousness perceives time as a continuous stream, yet the ongoing discourse in both physics and philosophy wrestles with whether this temporal flow reflects an inherent aspect of the universe or merely constitutes a construct of human cognition. Now, let's delve into the block universe theory. This theory, which has intrigued many in advanced cosmology, science, and philosophy, presents a distinctive outlook on the nature of time and our universe. Rooted in Einstein's theory of general relativity, it proposes that time is akin to a spatial dimension, much like the three dimensions of space we navigate. According to this view, past, present, and future exist concurrently, with the flow of time being more a facet of human perception than an intrinsic physical reality. Imagine the universe as an expansive four-dimensional block, where every moment in time is laid out alongside each other. This block universe encompasses all events, from celestial phenomena to everyday occurrences. Here, what we perceive as the past constitutes merely another segment of the block universe, possessing equal reality to the present and the future. The block universe theory prompts intriguing questions about causality and free will. If the future already exists within this four-dimensional construct, it implies a deterministic universe where forthcoming events are predetermined and unalterable. This notion challenges our typical experience of decision-making and influencing future outcomes, raising profound philosophical inquiries into the nature of free will and our place within the fabric of time. Furthermore, the block universe theory aligns with the phenomenon of time dilation, a fundamental prediction of relativity. According to relativity, observers in motion relative to each other or within varying gravitational fields will perceive time differently. In the block universe framework, these divergences in time perception represent distinct paths through the four-dimensional space-time continuum. This concept harmonizes with experimental findings supporting time dilation, such as the observed variations in time measured by atomic clocks on Earth and in satellites. Despite its intriguing propositions, the block universe theory faces skepticism from some quarters. Critics argue that it clashes with the apparent randomness inherent in quantum mechanics, the branch of physics dealing with subatomic particles. Quantum mechanics suggests an inherent uncertainty in the behavior of these particles, a feature seemingly at odds with the determinism posited by a predestined block universe. Could the universe exist devoid of time? Time fundamentally serves as a metric of change, a framework that delineates how events unfold and progress. In classical physics, time flows as a continuous river, steadily advancing. This perception aligns with our everyday encounters, where cause and effect unfold linearly. Yet, delving into the realms of advanced physics, time assumes a more intricate and elusive character. According to Einstein's general theory of relativity, time intertwines with the spatial dimensions, forming a four-dimensional space-time fabric. This fabric bends and warps under the influence of mass and energy, with time not merely a backdrop, but an active participant in the universe's dynamics. Consider the second law of thermodynamics, pivotal in understanding physical processes, which dictates that entropy or disorder increases over time in an isolated system. Sans time, such principles lose their significance, depriving us of tools to comprehend the universe's behavior. Time provides context to our experiences and underpins causality, the link between cause and effect. Without time, the notions of existence and change become nebulous or devoid of meaning. Consider the notion: is time truly quantifiable? And if so, what defines its smallest increment? Enter the Planck time, a subject that captivates enthusiasts of advanced cosmology, science, and philosophy. Named after Max Planck, the luminary physicist hailed as the progenitor of quantum theory, Planck time stands as a cornerstone in theoretical physics. To grasp the scale of Planck time, one must journey into the realm of infinitesimal and rapid measurements. Clocking in at approximately 5.39 yoctoseconds, Planck time defies comprehension. In this fleeting interval, light, the universe's speedster, barely traverses a fraction of a proton's diameter. Such a concept arises from the Planck scale, a frontier where the influences of quantum mechanics and general relativity converge. Here, conventional physics falters and classical depictions of gravity and spacetime falter. At the Planck scale, spacetime itself is postulated to fragment into quantized entities akin to pixels on a digital canvas. Planck time emerges from the interplay of fundamental constants in physics, including the gravitational constant g, the speed of light c, and Planck's constant h. These constants coalesce in an equation yielding Planck time, marking a theoretical threshold in time measurement. Yet it's crucial to acknowledge that Planck time eludes direct measurement with present-day technology. Instead, physicists employ it as a conceptual tool to fathom the universe's bedrock. In practical terms, the smallest time increments within our grasp are orders of magnitude larger than Planck time. Even the most precise atomic clocks can only discern changes in time on the scale of attoseconds, vastly surpassing the fleeting domain of Planck time. As we delve into the infinitesimal realm of Planck time, a fundamental question arises: how do the smallest building blocks of the universe interact with this minute dimension? This inquiry lies at the core of cosmology and physics, especially when examining the behavior of fundamental particles such as quarks and leptons, like electrons and neutrinos. These particles, essential for constructing everything in the universe, exhibit behaviors that challenge our conventional understanding of time, particularly when viewed through the lens of quantum mechanics. In quantum mechanics, particles don't adhere to our familiar linear perception of time. Instead, they operate within a realm of probabilities and uncertainties. A pivotal concept in this domain is the Heisenberg uncertainty principle, which asserts that certain pairs of properties, like position and momentum, cannot be precisely determined simultaneously. Similarly, there exists an intrinsic relationship between energy and time. At extremely minute timescales, approaching Planck time, there's a fundamental limit to how accurately we can measure a particle's energy. This uncertainty can lead to intriguing phenomena, such as the temporary emergence of particle-antiparticle pairs from the vacuum of space, known as virtual particles. These fleeting entities abide by the uncertainty principle, existing for incredibly brief durations. Moreover, in the realm of particle physics, the notion of time reversal, or T-symmetry, adds another layer of fascination. Under specific circumstances, the fundamental equations governing particle behavior remain consistent even when time is reversed. This symmetry hints that, at a fundamental level, the laws of physics might operate identically regardless of the direction of time. However, in our macroscopic world, we observe a distinct lack of time symmetry due to the second law of thermodynamics, which dictates that entropy tends to increase over time, establishing a direction for time's arrow. Expanding from our examination of how fundamental particles engage with time, particularly through the concept of time reversal, we embark on a deeper exploration of the broader implications of time symmetry in the physical realm. This symmetry, suggesting that the fundamental laws of physics remain unchanged, irrespective of the direction of time, holds profound implications for our comprehension of the universe. In theoretical physics, the concept of time symmetry suggests that a particle's behavior should remain consistent whether it moves forward or backward in time. This principle is not just an abstract idea, it's a fundamental concept that underpins many physical theories and models. For example, numerous equations in both quantum mechanics and classical mechanics exhibit time symmetry, meaning they would still hold true if time were reversed. However, despite this theoretical symmetry, the observable universe appears to lack such consistency in practice. We perceive time as flowing in a singular direction, from past to future. This apparent asymmetry finds its most notable expression in the second law of thermodynamics, which states that the total entropy or disorder of an isolated system can never decrease over time. This principle establishes the arrow of time, pointing from states of lower disorder to those of higher disorder. The idea of time symmetry in physics carries profound implications, one of which challenges our conventional understanding of time's directionality. It raises the intriguing possibility that at the most fundamental levels, the universe might not inherently favor any particular direction of time. This notion forces us to reconsider our everyday perceptions and prompts questions about the very nature of time itself. Could the forward progression of time be merely a construct of our perception, rather than an inherent property of the universe? Additionally, time symmetry plays a crucial role in theoretical models and experiments in particle physics, particularly in studies involving subatomic particles conducted at facilities like the Large Hadron Collider, LHC. Understanding time symmetry is essential for deciphering particle interactions. Many experiments deliberately test the time reversal symmetry of certain processes to delve deeper into the fundamental forces and particles composing our universe. Furthermore, the notion of time symmetry has sparked speculative yet captivating concepts in cosmology. Some theories propose the intriguing idea of a universe where time operated in reverse prior to the Big Bang. While these hypotheses remain highly theoretical and subject to controversy, they highlight the diverse array of possibilities that time symmetry introduces into our exploration of the cosmos. Now, let's revisit the central question posed in this video. Why does time progress forward, and could this progression be illusory? Delving into whether the forward march of time is a mere illusion immerses us deeper into the intricate realms of physics and philosophy. This inquiry connects back to our earlier discourse on time symmetry and the arrow of time, which are pivotal to our comprehension of the universe and our role within it. The ingrained perception of time's forward momentum is a cornerstone of human experience. We recall the past, but not the future, and we traverse from youth to old age, not the other way around. This unidirectional flow of time is so deeply woven into our daily lives that the notion of it being illusory appears almost inconceivable. However, as we venture into the realms of advanced physics, the certainty of this forward progression begins to waver. At the crux of this debate lies the very essence of time itself. In classical physics, time is envisioned as an unwavering stream, steadily coursing from the past through the present and onward to the future. This perspective aligns seamlessly with our everyday encounters and the macroscopic universe surrounding us. However, as explored in discussions on time symmetry within physics, the laws governing the behavior of fundamental particles at the quantum level do not inherently differentiate between past and future. These laws exhibit symmetry concerning time, implying that at the fundamental level, the directional flow of time may not be an intrinsic characteristic of the universe. This prompts both philosophical and scientific contemplation. Could our perception of time progressing forward be more a product of human consciousness or the workings of our brains, rather than an inherent feature of time itself? This notion gains support from the second law of thermodynamics, which posits that entropy or disorder within an isolated system typically increases over time. While this increasing disorder gives the impression of time moving forward, it doesn't necessarily imply an inherent direction to time. Some theorists suggest a thought-provoking possibility. At its most fundamental level, the universe might exhibit time symmetry devoid of any preferred direction. In such a scenario, our experience of time's forward flow could emerge from the laws of thermodynamics and the initial conditions of the universe, rather than being an intrinsic property of time itself. Expanding on our exploration of whether time's forward progression is illusory, we delve into the intriguing relationship between consciousness and our perception of time. This intersection delves into how our minds understand and interpret the passage of time, straddling the boundary between scientific inquiry and philosophical reflection. Consciousness, the awareness of one's own existence and ability to think, profoundly shapes our temporal experience. Our subjective perception of time often diverges from the objective measurements of clocks and calendars. We've all encountered moments where time seems to speed up during enjoyable activities or slow down during periods of boredom or anxiety. This variability underscores that our experience of time is not a constant stream, but rather adaptable and influenced by our mental states and activities. Neuroscience has embarked on unraveling the enigma surrounding our perception of time. Research indicates that distinct regions of the brain are engaged in processing temporal information, and our sense of time can be influenced by various factors, including attention, memory, emotions, and neurological conditions. For instance, Our focus on a task can lead to heightened information processing within the brain, creating the impression of time passing more slowly. The relative nature of time perception becomes apparent in critical situations where individuals often report experiencing events in slow motion. This phenomenon may stem from the brain entering a heightened state of alertness, processing information at an accelerated rate to facilitate rapid response to danger. However, intriguingly, studies suggest that this sensation is more related to how we recall events rather than how we experience them in real time. The brain stores more detailed memories during intense moments, resulting in a perceived extension of time when we later recollect the event. Philosophically, the correlation between consciousness and time perception raises profound inquiries into the nature of reality. If our perception of time can be so profoundly influenced by our mental state, it prompts reflection on the extent to which the passage of time is an objective aspect of the universe versus a construct of human consciousness. Transitioning from the intriguing interplay between consciousness and time perception, we naturally pivot to the role of memory in shaping our temporal experience. Memory, a cornerstone of consciousness, profoundly influences how we perceive time's passage, intertwining with our subjective sense of duration and the sequential arrangement of events. Memory serves as the repository of our past experiences, constructing a personal chronicle of our lives. This mental timeline profoundly shapes our perception of time. How we recollect events can greatly impact our understanding of elapsed time. For instance, periods filled with diverse and novel experiences may appear longer when remembered. This explains why, in hindsight, time spent on vacation or learning a new skill often feels more expansive than a similar duration spent on routine tasks. The richness and variety of experiences seem to elongate time within our memories. This phenomenon, termed the holiday paradox, illustrates how packed memories of fresh experiences can stretch our perception of time when we reflect upon them. Conversely, periods with fewer novel memories may seem to pass swiftly despite occupying the same amount of real time. Moreover, the emotional intensity of memories significantly influences our temporal perception. Events imbued with strong emotions, whether joyful, traumatic, or sorrowful, tend to be more vividly retained in memory. This vividness can impart a sense of prolonged duration to these moments in our minds. It's a common experience to feel time dragging during difficult or painful circumstances and speeding by during moments of happiness. Age also shapes our temporal perception through the lens of memory. As we age, the pace of forming new memories typically decelerates. This can give the impression of time accelerating with age, as fewer fresh memories are accrued over a given period compared to our youth. Childhood and young adulthood often feel elongated because they are marked by numerous first experiences and significant changes, all contributing to the accumulation of dense, vibrant memories. Additionally, our recollection of memories is not always linear. Events are often remembered out of sequence, and the frequency of recalling certain memories can influence our perception of their significance and duration within our mental timeline. Animals, akin to humans, perceive time, yet their perception can significantly diverge, influenced by factors such as size, metabolic rate, and ecological requirements. Smaller creatures with rapid metabolic rates, like birds and insects, tend to slice time into finer increments. This heightened perception allows them to process visual information swiftly, enabling rapid responses to environmental stimuli. A striking example is the fly, renowned for its ability to detect and react to movements far quicker than humans, seemingly possessing lightning-fast reflexes. Research indicates that this variance in time perception stems from differences in animals' nervous systems. The processing speed of an animal's nervous system shapes its temporal perception. Species needing swift reactions for survival, whether evading predators or capturing prey, have evolved to process information rapidly, elongating their perception of time. The lifespan of an animal also influences its temporal perspective. For creatures with shorter lifespans, like mice, a year constitutes a significant portion of their lives, contrasting sharply with humans for whom a year represents a smaller fraction. This disparity affects how animals perceive shorter time intervals. What may appear fleeting to humans could seem considerably longer to creatures with briefer lifespans. Furthermore, animals' temporal perception shapes their behavior and survival strategies. Migratory birds, for instance, synchronize their movements with seasonal changes linked to variations in daylight length throughout the year, demonstrating an awareness of longer temporal cycles crucial for survival. Intriguingly, some animals exhibit behavior suggesting an understanding of future events, closely intertwined with time perception. Squirrels hoard food for winter, while certain primates display tool usage indicative of planning for future needs. These behaviors imply a cognitive representation of future time, although it remains uncertain whether this stems from a conscious grasp of time akin to human experience. Exploring the connection between time perception in animals and the broader impact of time on aging and lifespan leads us to a fascinating convergence of biology, physics, and philosophy. Aging, a universal process among living organisms, is intimately entwined with the passage of time, offering insights into the essence of life and longevity. At its core, aging can be viewed as the cumulative effect of time on biological systems. Cells within an organism accrue damage over time due to various factors, including environmental stresses, genetic predispositions, and the inherent constraints of cellular replication. This accumulation of damage precipitates the gradual decline in physiological functions associated with aging. The pace of aging and an organism's lifespan are shaped by a complex interplay of genetic and environmental influences. For instance, smaller creatures like mice with faster metabolisms typically exhibit shorter lifespans, whereas larger animals like elephants with slower metabolisms tend to live longer. While the rate of living theory posits a correlation between metabolic rate and lifespan, it fails to fully elucidate the wide-ranging variations in lifespan across species, as exceptions abound. On a cellular level, the concept of telomeres assumes paramount importance in the aging process. Telomeres, protective caps situated at chromosome ends, undergo shortening with each cell division. Once telomeres reach a critically shortened length, cells enter a state of senescence or perish, contributing to aging. Intriguingly, certain species possess mechanisms to preserve their telomeres, potentially extending their lifespan. For instance, lobsters produce telomerase, an enzyme that rejuvenates telomeres, potentially bestowing upon them an extended lifespan. Moreover, the field of gerontology, dedicated to studying aging, has unearthed a plethora of genetic factors impacting lifespan. Certain species, like specific strains of laboratory worms and mice, have demonstrated notably prolonged or abbreviated lifespans due to distinct genetic mutations. These revelations underscore the significant role genetic composition plays in shaping an organism's longevity. In humans, aging emerges as a multifaceted phenomenon influenced not solely by genetics, but also by lifestyle choices such as diet, exercise, and exposure to environmental toxins. These lifestyle factors modulate the pace of cellular damage accumulation over time, exerting profound effects on overall health and lifespan. As we contemplate the impact of time on humans and other life forms, it prompts reflection on scientific breakthroughs that have reshaped our understanding of time and its complexities. Have there been pivotal discoveries in our journey to unravel time's mysteries? Indeed, numerous scientific breakthroughs have revolutionized our comprehension of this foundational aspect of the universe. These milestones span epochs, each contributing to a richer and more nuanced grasp of time. Among the earliest and most consequential breakthroughs was Isaac Newton's formulation of his laws of motion and universal gravitation in the 17th century. Newton's seminal work laid the groundwork for classical mechanics, wherein time was perceived as an immutable and absolute entity, flowing uniformly and unaffected by the motion of objects or the observer. This conceptualization of time as a distinct, autonomous dimension served as the cornerstone of physics for centuries. However, the most transformative revolution in our comprehension of time unfolded with Albert Einstein's groundbreaking theory of relativity in the early 20th century. Einstein's theory, encompassing both the special theory of relativity, 1905, and the general theory of relativity, 1915, wrought a profound paradigm shift in our perception of time. The special theory of relativity introduced the notion of time's relativity, illustrating that it can fluctuate for disparate observers based on their motion. This theory also birthed the iconic equation E equals mc squared, establishing a profound linkage between energy, E, mass, m, and the speed of light, c, thereby yielding profound implications across both physics and cosmology. Einstein's general theory of relativity further revolutionized our comprehension by revealing time's intricate entanglement with space, jointly forming the four-dimensional space-time continuum. This theory elucidated that massive objects induce curvature in space-time, resulting in what we perceive as gravity. These conceptual breakthroughs shattered the conventional notion of time as an immutable, unidirectional flow, portraying it instead as a dimension subject to the influences of gravity and an observer's velocity. Another notable breakthrough dawned with the advent of quantum mechanics in the 20th century. Quantum mechanics delves into particle behavior at infinitesimal scales, where classical physics laws may falter. Within quantum mechanics, time assumes the role of a backdrop parameter devoid of variability. This treatment of time diverges from relativity, prompting ongoing endeavors to reconcile the two theories within a unified framework. The emergence of exceedingly precise atomic clocks in the 1950s marked another milestone in our temporal comprehension. Leveraging atomic vibrations to measure time, these clocks have empowered scientists to scrutinize relativity's predictions with unparalleled precision. Experiments employing atomic clocks have substantiated relativity's forecasts, such as time dilation effects manifested by disparate time rates at varying altitudes attributable to gravitational influences. Moreover, the revelation and examination of cosmic microwave background radiation during the 1960s have yielded profound insights into the universe's age and evolution, granting a glimpse into the nascent epochs of time post-Big Bang. As we approach the end of our exploration, let us pause to contemplate everything we have encountered. What would a world bereft of time entail? Time constitutes such an intrinsic facet of our existence that contemplating a realm devoid of it is both captivating and intricate. In a time-null universe, the most fundamental alteration would be the absence of change itself. Time facilitates the progression of events, the causal chain, the unfolding of life's narrative, and the cosmos's evolution. In its absence, stagnation would reign. No growth, no decay, no motion, no evolution. The dynamic phenomena that define life and the universe, stellar birth and demise, galaxy formation, and Earth's cyclical life processes, would be nullified. Physically, the laws governing our universe would undergo fundamental alteration. Without time, the equations underpinning motion, energy, and gravity lose their coherence, rendering concepts like velocity devoid of significance in the absence of temporal metrics to gauge positional alterations. From a human perspective, a timeless existence equates to the forfeiture of history, memory, and anticipation. Our entire comprehension of reality hinges upon past encounters, present occurrences, and future prospects. In a realm sans time, aging and progression find no foothold. Life ceases to unfurl as a sequence of events. Notions of rhythm, routine, deadlines, and schedules lose their import, relegated to the annals of meaningless abstraction. Furthermore, a plethora of philosophical and existential inquiries emerge within a timeless realm. In the absence of temporal progression, do notions such as purpose, achievement, and progress retain any semblance of significance? Our pursuits, aspirations, and motivations are deeply entwined with time's flow and the capacity to effect change. In a timeless milieu, these quintessential drivers of human endeavor and societal evolution would be rendered inconsequential. The absence of time further implies a static and eternal universe, contradicting our current cosmological paradigm founded upon the tenets of flux and temporal evolution. From the cosmic genesis of the Big Bang to the unfolding of cosmic epochs to the present day. Continuing our contemplation of time, particularly the prospect of a world devoid of it, naturally prompts consideration of avenues for future inquiry to deepen our temporal understanding. Time, among the most fundamental yet elusive components of the cosmos, remains a focal point of investigation and intrigue across diverse scientific domains. A pivotal avenue for future exploration entails reconciling the twin pillars of contemporary physics, general relativity and quantum mechanics. General relativity, Einstein's framework elucidating gravity as the curvature of space-time wrought by mass and energy portrays time as a seamless continuum. Conversely, quantum mechanics, governing the microcosmic realm of atoms and subatomic particles, treats time as an external parameter distinct from the quantum states of matter. These discordant conceptualizations engender a profound theoretical impasse. A foremost ambition in physics is to forge a theory of quantum gravity capable of synthesizing these divergent frameworks, potentially unveiling novel insights into time's essence. Another pivotal realm of inquiry lies in the exploration of the early universe. By scrutinizing the conditions in the aftermath of the Big Bang, scientists aspire to unravel the genesis and evolution of time itself. This endeavor entails probing cosmic microwave background radiation, the residual echo of the Big Bang, and detecting and scrutinizing gravitational waves, ripples in space-time spawned by cataclysmic events in the distant cosmos. These investigations harbor the potential to furnish pivotal insights into time's character under extreme circumstances. Advancements in technology, particularly in temporal precision, assume paramount importance. Atomic clocks, leveraging atomic vibrations to gauge time, have heralded a revolution in temporal precision, empowering us to measure time with unprecedented accuracy. Subsequent innovations in atomic timepieces and analogous time-measuring instruments could facilitate even more precise experiments, scrutinizing relativity and quantum mechanics prognostications at unparalleled thresholds. Delving into black holes and their enigmatic event horizons presents another promising avenue for temporal elucidation. These cosmic behemoths, wielding immense gravitational influence capable of distorting space-time significantly, furnish natural arenas for exploring gravity's extreme temporal ramifications. The event horizon, the juncture beyond which escape is futile, engenders intriguing inquiries regarding time's essence vis-à-vis space and matter. Moreover, interdisciplinary forays encompassing neuroscience and psychology hold significance in deciphering human time perception. Such interdisciplinary endeavors harbor the potential to yield insights into the intricate interplay among the brain, consciousness, and temporal perception. Lastly, cosmological advancements facilitated by scrutinizing the universe's expansion and delving into the enigmas of dark energy and dark matter offer glimpses into the cosmos's future trajectory and the role time will play in its ultimate denouement. As we approach the culmination of our temporal exploration, we find ourselves immersed in a rich and intricate tapestry of ideas, theories, and revelations that collectively illuminate this quintessential aspect of the cosmos. From ancient astronomical observations to contemporary frontiers in physics, our odyssey through time has been nothing short of a profound voyage through the very essence of existence and reality. We've witnessed time, once perceived as immutable and absolute, unveil its fluid, relative nature, becoming deeply entwined with the very fabric of space-time. Einstein's groundbreaking insights into relativity have shattered conventional paradigms, revealing a universe where time warps and flexes, challenging our deepest intuitions. Moreover, the enigmatic realm of quantum mechanics has introduced layers of intricacy, portraying a cosmos where time's dominion may wane even at the minuscule scales. Ultimately, time transcends mere dimensionality. It embodies a narrative to be experienced, a puzzle to be unraveled, and a riddle to be contemplated. As we stand at the precipice of knowledge, gazing into the cosmos, we are humbled by our infinitesimal, yet consequential role within the vast expanse of space and time. Our journey, from the cosmic to the quantum, from the philosophical to the pragmatic, continues to ignite wonder, provoke inquiry, and evoke awe. It is an expedition that mirrors time itself, unceasing, boundless, and pregnant with the promise of newfound insights and profound revelations.